Welcome back to module 16 of where we are discussing attosecond charge migration. Its experimental setup has been discussed so far, and we have seen that XUV beam is produced with the help of high harmonic generation process. In the high harmonic generation process, in the experimental setup which we have here is the one XUV spectrometer, one filter for the XUV beam, and one gas cell here situated here. Now these are the components which we use for the XUV spectroscopy. This is the real lab image. This is the gas cell which is inserted inside this tube, inside this chamber, and then there is a hole here in this point, then there is another hole here in this point, and then the chamber. So chamber 1 and chamber 2 are actually used for the differential pumping, and the high harmonic separation chamber is actually situated here, this one high harmonic generation chamber, and this is the this is the spectrometer. So we have built this, a grating is kept here and the CCD camera is kept here. So this is the spectrometer, and we have said that previously that typically HHG spectrum should look like this. I have one intensity should drop down like this, and then there will be a plateau of intensity, and then there will be a cutoff. This is the typical intensity, and this way you are plotting, let's say, energy EV, and this way you are plotting intensity. So this is the typical HHG spectrum, what it should be. But when we looked at N2 spectrum, this is the N2 spectrum, which means in the gas cell we have injected N2 gas, we have filled with N2 gas. When we looked at N2 spectrum at this 10 to the power 15 watt per centimeter square high intensity, I mentioned that high intensity we need to tunnel ionize it, and then once I tunnel ionize it, electron will be traveling in the field and it will recombine. So this is a strong field effect which we see in the HHG process. Now when we look at the N2 spectrum, our spectrum is this red color spectrum, which is quite different from what is expected from the HHG spectrum. It doesn't have plateau, it doesn't have fast decay, and it does, but it has a cutoff. This is the cutoff. After this energy we do not see anything. So we see the cutoff, but we do not see any plateau, and we do not see any decrease in the first few harmonics. And it's because we are using aluminum filter. So once we have used aluminum filter, what we see, this is the transmission curve which is shown here. These curves are transmission curves, which means that how much XUV beam will be transmitted through the aluminum filter. This black color is actually transmission characteristics of the aluminum filter, and in the aluminum filter what we see is that up to 15 EV nothing will be transmitted due to presence of the aluminum filter. Aluminum filter will transmit only light above 15 EV, and that's why below 50 EV, 15 EV will not see anything. But at the same time we have to understand that when you take an aluminum filter, we say that it is an aluminum filter, but we have any metal we take, if we take iron, if we take aluminum, if we take let's say titanium or gold, which I have in my ring, any metal I take, due to the oxidizing environment or the atmosphere oxygen, the top surface will be always coated by its own oxide. It is a general behavior of any metal we take in the atmosphere. So this aluminum filter also exposed to the atmosphere. So obviously, although it is an aluminum filter, but its surface is actually coated by is now coated by a thin aluminum film, Al2O3 film. So this red color one, so this blue color one is Al2O3. This is the oxide of aluminum, and inner material is still aluminum. So, we have to understand the transmission characteristic of alumina Al2O3 film as well, but we do not know, unfortunately we do not know what is the thickness, typical thickness of that Al2O3 film on that filter. But if we take a, let us say, general gauge, that is it's 30 nanometer, let us say, or 400 nanometers. So, this thickness, this aluminum thickness, when we purchased this aluminum filter thickness was 600 nanometer. In the 600 nanometer thick aluminum foil, we may have, let us say, 30 nanometer thick aluminum film. And if we have aluminum film, we see that from 20 EV to 40 EV or 50 EV, it is a slopy increase in the transmission. And that is exactly what is showing up here. 20 to 40 EV is a slopy increase in transmission. So, this slopy increase in transmission is due to the filter which we use. It is not because of the behavior of the HHG. So, we had probably, if we could somehow analyze the whole spectrum, whole light without filtering it, without using the aluminum filter, we could have observed a plateau here in this regime. But we do not see the plateau because the transmission of Al2O3 is a slopy, or it's slowly increasing as we go to the higher energy photon, and that's exactly evident here. 20 to 30 EV or 20 to 30, 20 to 40 EV, they are slopy increase, and then this decrease is due to the cutoff. So, this decrease we understand it is the cutoff regime. So, this is your cutoff regime, which is nothing but in this regime, but this slopy part is due to the filter which is affecting the transmission. So, that's the reason why in the end what we observe is actually a spectrum which looks like this red color spectrum, and all the spectra we observed from different gas molecules, they actually follow similar kind of this kind of patterns, this red color pattern. In the background, this black spectrum is actually simulated spectrum, and in the simulated spectrum we see that the cutoff is matching, but then slowly this part is actually not matching, and this part is not matching is because in the simulated spectrum we do not use any filter. It is actually theoretically simulated spectrum which shows a plateau. So, from this point it is a plateau, it is supposed to be a plateau, but we do not see the plateau because of the transmission of this transmission characteristics of the filter itself. So, with this idea we started working on this system, and we remind ourselves that our target system was two dissimilar molecules, two different molecules weakly bound together. Here we are using, one of them is chloroform this molecule, and another molecule is acetonitrile, this molecule. So, these two molecules are weakly bound together by a dotted line. This dotted line is the non-covalent bonding interaction. Any molecule in this room, if they are interacting with each other, but their interaction is very weak, they are very weakly interacting, and this interaction energy the interaction, the way it is interacting is called non-covalent interaction. So, this minimum distance which is achieved by the equilibrium optimization of this cluster is this distance is called non-covalent bond distance. This is the minimum distance which we can have between these two molecules, and they are weakly bound by this interaction. Now, what is this interaction? This interaction is an interaction between hydrogen and a nitrogen of two different molecules, hydrogen from chloroform and nitrogen from the other molecule. These two molecules are interacting, and we know that these two molecules having different ionization potential. Ionization potential of this guy, this molecule is IP is greater than this molecule. So, IP of this molecule is low, and because this is a low ionization potential, I remove an electron from this molecule. Even they are bound together, because this molecule having lower ionization potential than this molecule, when I remove an electron, when I undergo this tunnel ionization, preferably electrons will be removed from this molecule only. And once we remove an electron, we know that we create a hole, and that is the hole density we have shown at the point of 0 attosecond time scale. And this hole density, if we allow to relax, what does it mean? I have a bucket of, let us say, electrons. In a molecule, I have lot of electrons, and I remove an electron from there. If I remove an electron from there, the whole field has changed. Electrons are charged particles, they are interacting with each other. So, once you remove an electron from that molecule, the whole electron density has to reorganize one more time, because the field, effective field, the mean field has changed. And due to this, during this reorganization, I can have this charge migration. The whole charge which I have created only in the chloroform moiety, it is moving towards the acetonitrile moiety in 200 attosecond. And then again, if we look at 600 attosecond, it is actually the maximum change we see. So, what is evident from this theoretical investigation, which is a continuation of the previous theoretical presentation which we had previously also in the previous lectures, that I have two molecules weakly bound. I have removed electron from this molecule, and that molecule, due to removal of an electron from this molecule, I have created a whole charge in this. That charge is now delocalizing. It's moving to the both side of the molecule. So, it's delocalization of charge, and this delocalization of charge occurs within 600 attosecond. Now, question is how this is going to affect the HHG process. In order to understand that, what we have used is that we have taken binary mixture of chloroform acetonitrile and chloroform methanol. If we look at this molecule is retained. In the previous slide, we had this molecule, but instead of taking this molecule, we have changed the molecule to methanol. Two different molecules. Binding energies are almost equivalent, 4.96 kcal per mole for one of them and 5.59 kcal per mole, kilocalorie per mole. That's binding energies are almost comparable, equivalent binding energies, and it has been clusters observed through FTIR at the room temperature. These clusters, they form the clusters that was evident through the FTIR spectrum. So, FTIR is pointing out that those clusters are present even at the room temperature, and their binding energies are comparable. So, they can exist being weakly bound. Question is, when I have changed, so this molecule was fixed, this molecule was chloroform, but this molecule, instead of acetonitrile, we have used methanol. These two combination, when we checked, we have found that no charge migration occurs. Theoretically, we have found that no charge migration occurs from one end to the another end in this combination. And this is an interesting theoretical observation. In one combination, when I have acetonitrile, I have chloroform and acetonitrile both together, I see charge migration, attosecond charge migration. When I have chloroform and methanol, then I do not see any charge migration. This is the prediction we get from theory. And after getting this prediction, we thought that if we try to observe high harmonic generation from these two different systems, one may respond in a different way, another may respond in a little different way. So, we wanted to check the differences between these two systems. In order to check that, what we have found is that at the 4-star gas cell pressure, we said that we have a gas cell first. In the gas cell, then we had another chamber where we have a hole here. So, this is also, there is a hole here also in the gas cell. We have a hole, collinear hole, and then there is another hole. So, this the three holes we have, and then the beam, light beam is propagating through this medium. This gas cell has a window. Now, this gas cell pressure is varied, and we see that at the gas cell pressure of 4 torr we do not see any signal for HHG. HHG is not produced when individual gas cell pressure is 4 torr. At the 4 torr we do not produce it. But when we mix them, let us say 3 torr, if we mix them 3 torr acetonitrile 3,2 chloroform, we see an enhancement in the signal, and if we try to mix them with 3 torr chloroform 3 torr helium, we do not see any enhancement. And also instead of helium, if we use methanol, also we do not see any enhancement. So both methanol, helium, many other gas molecules are not doing enhancement in the signal. The only enhancement we see is due to acetonitrile chloroform. Acetonitrile chloroform is therefore having an unique property with respect to other gas combinations. Now question is, why there should be a pressure dependence in the HHG yield? Previously we have discussed this one, that HHG process is nothing but a nonlinear process, a nonlinear frequency conversion, and in any nonlinear frequency conversion we have to understand the phase matching behavior, because phase matching is the only factor which will control the efficiency of that conversion. Whether I will see a new light or not, that depends on whether I have achieved phase matching or not. So what is phase matching? Here I have given an example one more time, taking an example of SHG, second harmonic generation. Second harmonic generation is not produced through HHG, because HHG cannot produce any even harmonics, but we will take an example of SHG just to remind ourselves. So what happens, I have a medium, let us say I have a medium of this thickness, and the beam is propagating from this direction to this direction, beam is propagating. Now in the medium, this is a dielectric medium. Dielectric medium, what does it mean? It does not have any free electron like metal, it does not have any free electron. So what happens, this when the fundamental beam is propagating through this medium, in this regime, in the beginning I create a polarization, and also in the end I create a polarization, because beam is propagating through the medium. So I am just considering two different dipole, one dipole in the beginning of the interaction and another dipole in the end of the medium, these two dipoles. Now dipoles, oscillatory dipoles are actually the source of electromagnetic radiation, and that is creating the new light. So what will happen if this dipole is creating an electromagnetic radiation which is propagating, and this dipole is creating another electromagnetic radiation which is propagating? If these two electromagnetic fields are in phase, then we call phase matching is achieved, and phase matching is achieved, and that's exactly exemplified here. See, each dipole is creating new field, and those fields are in phase, and that's why it is phase matched. But if each dipole is creating the field and each field is not in phase, they will cancel each other, and once they will cancel each other, I get zero output. So there is a nonlinear effect in the medium, but output would be 0. So output in this regime would be 0, just like this, and this regime I have some output because I have been able to achieve phase matching. Now the medium which we use here is gaseous medium and partially ionized medium. So basically it is a partially ionized gas medium which we use. Partially ionized, why? Because due to strong field ionization I am ionizing the medium as well. So I have neutral molecules as well as plasma medium as well. It's a mixture of plasma and neutral. What is plasma? It is fourth state of matter. I know the matter, different states of matter: solid state, gaseous state, liquid phase, and plasma phase. Plasma phase is one phase which is creating lightning during rainy season. So plasma phase is nothing but an ionized phase, a gas molecule which are highly ionized. Electrons, radicals, they are put together. That's a very reactive state. of matter. And when we look at the phase matching in the nonlinear optics, we have come to know that we have to think about the magnitude of the wave vector and how does it depend on the medium refractive index. We know that 2 pi by lambda, this part is coming from the vacuum contribution, always there for the vacuum field. Then this part is due to the neutral dispersion. Then this part is due to plasma dispersion. This is neutral dispersion. This is neutral dispersion. This is plasma dispersion, and this is your nonlinear dispersion. So these are the terms we have. Interestingly, we see that for each term I have P, P and P. P is nothing but the pressure, which means that pressure is going to contribute to the overall phase matching of the for this high harmonic generation. And we see that the plasma dispersion has a negative term, neutral dispersion has a positive term, which means they will just act in opposite direction. And two factors, when I am increasing pressure, two factors will contribute in opposite direction, which means one of them is trying to break the phase matching, another one is trying to bring the phase matching. And in an equilibrium, at a we will get an optimum point, optimum pressure, at what point we will get the maximum yield. And that is why I see pressure has a maximum value here, always a pressure which will give me the optimum HAG yield. So when we see a pressure dependent study, when we see a pressure dependent behavior in HAG, always we think that it could be because of the phase matching problem. Now, if it is a simple pressure dependent phase matching issue, then we could have imagined that when we used chloroform and helium, chloroform, methanol, chloroform with other molecules, all the molecules should have similar kind of behavior, because I am increasing the pressure to the same level. So, it should show me the efficiency, but we do not see that. We see only chloroform and acetonitrile. This combination is giving enhancement in the HAG yield. In fact, it is giving you HAG efficiency. But any other combination, you take out this acetonitrile and use methanol, use helium, use any other molecules, is not giving the enhancement HAG yield. So, it cannot be pure pressure dependent phase matching, which we very easily conclude for the HAG process. Second thing, second point which we should clarify is that, okay, if it is not pure pressure dependent phase matching, then what is contributing to that enhancement? So, to understand it, we use quantum mechanical time dependent Schrodinger equation, simulation based on time dependent Schrodinger equation, and the problem is very simple quantum mechanical problem. I have an electron which was bound to the molecule first, then that electron is removed, or that electron is actually sent to the continuum. So, it was actually went to the continuum state, it is not localized anymore, it is continuum, and then again during recombination is coming back. So, the whole problem is that I had a localized electron, it is going to the continuum and again coming back and recombining. So, I have an active electron, and the wave function of that active electron is psi xt. This is the time dependent Schrodinger equation. I have kinetic energy component, I have potential component, I have external electric field component. And what is that potential? Potential is nothing but the molecular electrostatic potential. When electron is away from the cation, this cation has its own electrostatic potential. Its electrostatic potential, it means that it is actually affecting the electrostatic environment of the system. So, this is the molecular electrostatic potential which we can define. Molecular electrostatic potential is the interaction. So, interactions between, so I have in an let us say I have an atom. In an atom I have a nucleus, and then I have lot of electrons here, and one of the electrons I have removed. So, I have removed this electron, let us say. This electron is making a journey going away and then coming back and rejoining it. When it is doing it, then the electrostatic potential which is calculated is actually an interaction between this electron with the electron density at this point. Electrons are not particle anymore, electrons are actually represented by its own density. So, I have to find out the electrostatic interaction between electron density and this electron, and that is represented by this term, and electron will be interacting with the positively charged core nucleus as well. So, this electron will be interacting with this. So, this is the electrostatic potential between electrostatic potential represented by this, and this is the electrostatic potential represented by the interaction between the density at that point with the electron, incoming outgoing electron, and that is the electrostatic potential. So, with this electrostatic potential, this is the electrostatic potential, this is the kinetic energy operator in one dimensional problem, and this is the electric field under which it is undergoing the acceleration. Finally, if we solve this equation numerically, then I get x t value at different time, psi x t value. If I plug that in this dipole acceleration term dt term, then what I get is actually the spectrum is square modulus of Fourier transform of, this is Fourier transform of dt. So, that I get in terms of omega. That we have seen always. If I have time dependent part, I can convert to frequency dependent part, and spectrum is nothing but the square modulus of the Fourier transform of the time domain part, and that is the way we get the spectrum. So, dipole acceleration term is used for that, and we see that in the dipole acceleration term we have a derivative term, that is with respect to x v is changing. And why I should have a change in the spectrum is because now we see that this dipole acceleration term is affecting. So, once I remove an electron from here, when electron is making the journey away from it and then coming back to this, during the comeback it does not see this electron density, is actually seeing this electron density. So, there is a change in potential, and due to this change now I have the enhancement in the spectrum, in the HIG spectrum. So, with this there are many conclusions one can make from both from theoretical work which we have done and experimental work which we have done. The conclusions are following: attosecond charge migration in weakly bound clusters is a route to study dynamics of chemical bonding. We can monitor time dependent change of electron density. So, we have to focus on weakly bound clusters, because weakly bound clusters gives an opportunity to remove an electron selectively from one moiety and to see how electron density is reorganizing after removing an electron from that from one moiety. So, this is already evident, and we would like to continue this work with the different kind of van der Waals complexes, halogen bonded complexes, tetrahedral bonded complexes, different weakly bound species. Attosecond charge oscillation followed by a few femtosecond damping is common to all. We are always seeing that. So, once I remove, if I take an equilibrium geometry, one geometry which is an equilibrium geometry, and if we remove an electron, I see always an oscillation, and that oscillation will be damped because equilibrium geometry is not the only structure which we see in at the room temperature. If we consider room temperature, we can have this structure, we can have this structure, we can have this structure. There are many combinations, and that's due to the fact that first vibrational state, ground vibrational state, is represented by a Gaussian. Center of the Gaussian is the equilibrium geometry, but it has many other configurations as well, and one can sample the different geometries from Wigner distribution. Many other ways one can sample it and check how this width, finite width of the vibrational wave function before ionization can affect it. We see that it can actually damp the oscillation. So, this oscillation can be probed with the help of different center wavelength for HHG. That is one conclusion we have made. Driven by relaxation and exchange interactions, we have seen that this charge migration between these two weakly bound species is driven by relaxation and exchange interactions, and because it is driven by exchange interactions and relaxation, one can think of studying dynamics of long and short range exchange interactions. These are very important for cold chemistry. When I have two species, how they are interacting with each other, that's an important question. I have neutral species, let's say I have a neutral molecule, and one ion, let's say positively charged molecule, is going through the neutral molecule, let's say. And when it's going through the molecule, near the molecule, in the near vicinity of this molecule, they will interact with each other. They may exchange charge. And one can think about, okay, what is the typical distance of that exchange of the charge? Can I go this way and still they can exchange? Can I go this way and still they can exchange? So these are the dynamics of long range and short range exchange interactions, which are very important for fundamental physical chemistry, that can be studied with the help of this relaxation and exchange interactions driven attosecond charge migration. And finally, we have already shown that HHG cell probing spectroscopy is very sensitive to the attosecond charge migration. Is it the only technique? Can we use femtosecond, attosecond palm probe photoelectron spectroscopy as another alternative route to the investigation of this attosecond charge migration? So with this big hope and little conclusions, we will stop here for this module. We'll meet again for the next module.